My name is Bill Kinney, and this is Quick Precalculus Review for Calculus, Part 4. Also Part 4 of a unit focusing on comparing and contrasting linear and exponential functions. We haven't gotten to exponential functions yet. I hope to do that in the next video or two. But in this video, the math that we're focusing on is describing how linear functions change. We started describing that in the last video, Part 3, and I'm going to continue that in Part 4. That's going to be my main mathematical emphasis. I'm doing everything in the program called Mathematica, and I've got some things I'm going to do with Mathematica in this video as well. We're going to talk about naming things in Mathematica, giving both lists of points and graphs names, storing them in a variable. We will talk about graphing lists of points in Mathematica with ListPlot, and we will also talk about combining different plots in Mathematica with another command called show. We've considered two examples. One of them is a population growth and another is a depreciation example. I am going to think about both examples in this video. Let's quickly review what we learned in the last video about the population growth example, which we were modeling as a linear function. We came up with this particular linear function as an approximation to the population of Austin, Texas as a function of time, where t is time in years since 2010, and the population p was given in thousands of people. At the end of the last video, we focused on symbolically trying to understand how this function changes, how the dependent variable changes as the independent variable changes. Before I get into that again, I want to say just a comment here about a point of view you want to have to be successful in calculus. People who are good at describing things in calculus often use phrases that imply motion, a dynamical approach to things. They'll say things like, let t go to infinity, or let x approach 0. They'll use phrases like that. They'll say, let x change by a certain amount. What's going on there? What they're really doing is they're using their imaginations, okay? The math that they write down is static, but they're using their imaginations to imagine that variables are changing and quantities are changing, they're increasing, they're decreasing, they're changing at different rates. That dynamic picture of calculus is essential. So you want to use your imagination. Let's take a look at this equation, this what we were thinking about at the end of the last video, and try to use your imagination to understand this. T, we're imagining letting the independent variable, which I called t, to change. I'm also using here initially the letter t to represent the initial value of the independent variable, and I'm imagining that that amount changes, that variable changes by an amount that I'm calling delta t, which represents one quantity. So imagine a number line, maybe go ahead and draw it, mark off a point on that number line, imagine that that is a number that you're calling t, and then you're letting that change by a certain amount, delta t. Imagine delta t is small, like 0.1 or 0.2 or something. So that means the point is moving to the right by that amount. Delta t can be negative, so you'd move to the left. If you added a negative number, you'd move to the left on the number line. Use your imagination to try to actually imagine that. What's going to happen to the output of the function? How much will p change by? That's what we're trying to imagine here. Delta p is the new value of the function at the new input t plus delta t, represented by this symbol, f of t plus delta t, minus the old value of the function. That difference, f of t plus delta t minus f of t, is the change in the function value, symbolically speaking. We can do the algebra, use our algebra skills to simplify that, and the main point here was that delta p, the change in this linear function, the output, for a given change in t, delta t, is proportional to that change. It's a constant times delta t. 31.7 is the constant of proportionality. That is the slope of the graph. It's the rate of change. It's 31.7 thousand people per year. So as you change the number of years by a certain amount, you multiply it by 31.7 thousand people per year. The years cancel, you get a certain change in the number of people, thousands of people in this case, delta p. Would we get the same kind of thing if we applied this to the depreciation example? Here is the depreciation example. New car is bought in 2013. The initial price is $24,000. 1 year later, its value has gone down. It has depreciated to $21,000. And here was the formula we got for this function. And by the way, I probably should name this function something different, like g, to distinguish it from the f that's above. So there's our formula for this situation. Again, this is a model. It doesn't necessarily model reality perfectly. But here we want to ask again, what happens as t changes? If t changes from a number t to some other number t plus delta t, what is the change in v? What is delta v? Let's do the same kind of calculation we did in the last example. Again, my function name this time is g instead of f, so I write g of t plus delta t. Again, delta t is one quantity, minus g of t. This is the new value of the function at this new input, minus the old value of the function at the original input. Algebraically, what happens when you plug these expressions into this function? In this case, t plus delta t, the entire thing inside the parentheses, gets plugged into the function in place of t. So we get 24 minus 3 times t plus delta t. This is a function input. This is not g times t of t plus delta t. It's g of t plus delta t. This right here, though, is a multiplication. That's 3 times t plus delta t in parentheses. You need to make those kinds of conceptual distinctions if you're going to be successful. Minus g of t, which is minus 24 minus 3t. Notice I'm using parentheses. I want to subtract that entire expression. That's g of t right there. Now I use the distributive property in a couple places to simplify this. The 3 distributes through the parentheses here. G, by the way, does not distribute through the parentheses there. That's not a multiplication. That's g of t plus delta t. The minus sign does distribute through the parentheses because I'm really adding negative 1 times that thing, and so I distribute the negative 1 through to get minus 24 and a plus 3t. The 24's cancel, the 3t's cancel, and the only thing you're left with is this negative 3 times delta t. Negative 3 times delta t. There we have it. The same kind of thing is happening. The change in the dependent variable is proportional to the change in the independent variable. The constant of proportionality in this case is negative 3, which is the slope. It is the rate of change. The units here for the slope would be in thousands of dollars per year. So if you multiply that by the change in the number of years, the years would cancel, giving you a change in the value in thousands of dollars. All right, that's the main mathematical point I want to make in this video. Let's get to doing some things in Mathematica to finish off the video. Naming things in Mathematica, graphing list of points in Mathematica with ListPlot, and combining plots in Mathematica with show. Alright, I showed you in the last video that you can enter functions in Mathematica like this, and you can use table to create lists of points in Mathematica. And then you can display those points with table form and table headings in this way that I'm showing you right here. I want to show you that you can name things in Mathematica, for one thing here. For example, I could name this list of points, well, I could call it points. I could type the word points here, I could type an equal sign, it's a little slow. Enter that, and now that list is stored in the variable that I've called points. If I type the word points here and enter that, I see the list of points again. If I type something else like just the word point, there's nothing stored in point, so I just get point back. I can clear that list, so now nothing is stored in points, but then I can re-enter the list and see that that re-entered list is stored in points. I can, since I have that stored in points, I can replace this table thing right here in the table form with the variable name to reproduce the table. If I put a point in here instead of points, I'd probably get some kind of error, or I get nothing. Alright, let's put it back in there. You can plot points. You can plot a list of points with ListPlot. Here's the basic syntax. Okay, there's my list of points. I can put it inside ListPlot to plot those points. There they are. They are on a straight line. I can add options to this as usual. One thing I like typically doing is making my points black and making them bigger with something called point size. I usually pick 0.03. That's an option that makes your points bigger. I can name this plot. I can call it a plot of points. If I spell it right here. Now that graph is stored in the variable plot of points. And if I enter that, I get the plot back. I can clear it out. And now if I enter it, I get nothing. I just get the name back. I can re-enter it and enter the plot of points and see the graph again. I'm going pretty fast here. I hope you're following it. You may want to rewind and watch it again. I can combine graphs. Okay, here's the final punchline with something called show. I can combine this plot, this line, with my plot of points. I can type plot of points here, put a comma, and then put an n square bracket for the show. Let's see, yeah, n square bracket. So I've got two things inside the show. I've got two arguments. The first argument being this plot of points, which is the variable that has the graph, this graph shown in it, or is stored in it. And this plot was my original plot that looks like this. I want to combine these plots with show, separated by a comma. There they are, though my plot range went goofy on me. I think if I copy and paste this plot range outside of the plot, but still inside the show, it will change it perhaps. Oh, but then it put the origin in the wrong spot. Sometimes this is unpredictable to me what's going to happen, but it can be fixed. Axis origin, arrow 0, 0, we'll put the origin at 0, 0. Okay, so there's lots of different things. I see it did get rid of the plot label as well. Alright, I'll put that outside of the plot, but still inside the show. I guess I'm glad that these things happened here. Need a comma right there. There we go, there's the plot labeled as well. Okay, so I went pretty fast, but I showed you a lot of important things, so you might want to rewatch the last few minutes to make sure you understand how to do all these things in Mathematica. If you don't have Mathematica, I still hope you got a lot out of it. I guess I will show you one more thing, sorry. I'll show you that the order matters here as far as the show goes. These dots are sort of behind the line segment there. If I put the plot of points after the regular plot, like right here, it will put them on top of the line segment because it's second. There we go. That's probably better. Okay, I'll end the video there.